Welcome to my talk on neural correlates of augmented feedback processing. We scrutinized if they are associated to short-term behavioral changes and automaticity in motor learning. Motor learning is accompanied by a change in the coding of representations that are relevant for motor control, as well as a shift of neural substrates underlying more attentional control in early phases and automatic control in later phases. This reduction in the need for attentional motor control is termed motor automatization and can be measured as the reduction of dual task costs. Dual tasking induces an increase of errors, which is reduced after extensive practice. Our recent studies on learning a motor sequence task revealed evidence that the valence of augmented feedback modulates attentional control and automatization. We were able to show that high frequent negative feedback led to persistent dual task costs even after extensive practice in 5 sessions, whereas reduced frequencies of error feedback enables automatization, and conditions with frequent positive feedback facilitated automatization, which can be explained by dopamine-mediated long-term potentiation, according to the reward prediction error hypothesis of dopamine. Error processing, which might induce attentional control, is reflected in different event-related potentials. The feedback-related negativity, FRN, is assumed to reflect prediction errors within reinforcement learning and is associated to a disinhibition of the anterior cingulate cortex as part of an attentional cognitive control network. The FRN has been shown to predict short-term behavioral trial-to-trial changes in conditions with low complex feedback as binary feedback. In contrast, the late fronto-central positivity is associated to supervised learning where the current outcome is compared to the desired outcome. The LFCP has been shown to predict behavioral changes when error direction and magnitude is available. We hypothesize that short-term changes are higher after higher amplitudes of the FRN and LFCP. For motor automatization, we assume that higher amplitudes induce more attentional processing and therefore less reduction of dual task costs. 38 participants learned an elbow extension flexion sequence with 3 movement reversals on a potentiometer-based arm lever device. The goal was to hit the reversals as precisely as possible and keep the movement time below 1800 milliseconds. We conducted 3 test blocks with a dual task procedure. During the intervention phase, there were 5 practice sessions with 960 tries of practice. EEG was recorded in the first and last practice session. During practice, feedback was given as an error bar for the deviation of the largest error of the 3 reversals. The bandwidth feedback for positive feedback and the rewarding score was adapted based on the performance of each preceding block of 12 trials. During the dual task blocks, the participants performed the motor task with an attentionally demanding NMAC task in single and dual task conditions with an interlaced order of tests. Behavioral results show a decrease in absolute and variable errors. Moreover, the analysis of the NMAC task reveals an interaction of time and condition, which reflects a reduction of dual task costs that is interpreted as motor automatization. We found higher amplitudes for the feedback-related negativity as well as for the late fronto-central positivity. Basically, this is also the case in practice session 5. The analysis of the FRN and short-term behavioral changes shows that trial-to-trial reduction of the maximum error is more reduced after negative feedback, while the amplitude of the FRN does not affect the error reduction within the positive or negative trials. In contrast, the goal-independent change of behavior is predicted by the amplitude of the FRN after negative feedback. The LFCP-amplitude predicts goal-directed change of behavior. Higher positivity after negative feedback is associated to a larger goal-directed change, meaning a higher reduction of the movement error in the following trial. The goal-independent change of behavior is not predicted by the amplitude of the LFCP in either of the 2 valence categories. Automaticity, measured as the reduction of dual task costs, is not correlated to the FRN. In contrast, dual task cost reductions are significantly correlated to the LFCP after positive feedback. The respective correlation of the LFCP after negative feedback just fell short of significance. As expected, short-term changes in behavior were predicted by the ERP amplitudes after negative feedback. Here we find a dissociation. The FRN reflecting reinforcement learning is associated to the goal-independent measure of trial-to-trial changes, whereas the LFCP reflecting supervised learning is associated to goal-directed changes in the following trial. We expected that the FRN, which is related to a cognitive control network, is negatively correlated to motor automatization. This was not the case. This finding should be challenged in experimental conditions with low complex feedback where reinforcement learning seems to be of higher significance. For the LFCP, we also assumed that a higher amplitude is associated to a less pronounced reduction in dual task costs. In fact, high amplitudes of the LFCP in the early practice phase were associated to a higher degree of automatization in the long term. We assume that participants who profoundly used quantitative error information early in practice established stable motor representations early in practice, which might facilitate an early transition to a learning phase with a reduced dominance of attentional processing. Thank you for your attention.